All right, today we're going on a pretty wild journey. We're diving deep into an invisible universe, one that's absolutely critical to modern science, the world of particle simulation. We're going to peel back the curtain and see how physicists build these incredible virtual worlds to predict how tiny subatomic particles behave.
So that really is the big question, isn't it? How in the world do you track something you can't even see? Something that moves at almost the speed of light and plays by the bizarre rules of quantum physics. I mean, how do you build a virtual microscope powerful enough to see the unseeable? Well, it turns out you need a very, very smart rulebook.
And that rulebook has a name, Geant4. Now, think of it less like a single program and more like a massive Lego set for particle physics. It gives scientists all the pieces they need to build a virtual world, the materials, the shapes, the laws of physics, and then they get to fire particles through it to see what happens. It's the gold standard for this stuff, used all over the world.
To really get how this all works, we're going to follow the life of just one particle. Think of it as the main character in our story. We'll follow it from the moment it's created as it takes its very first steps inside this virtual world. The whole process is called tracking. So every single particle in this simulation gets what's called a track, or in the code, a G4 track. The best way to picture this is like a passport. It has all the vital, up-to-the-second information about our particle, what it is, where it is right now, which way it's headed, and how much energy it's packing. And just like a real passport on a long trip, this thing is constantly being updated. Now, if the track is the passport, then a step, a G4 step, is like a single visa stamp in that passport. It's not the particle itself. Instead, it's a record of a tiny piece of the journey it just completed. It's a little snapshot that says, okay, I started here and I ended here. It's the fundamental unit of movement in this whole simulation.
Okay, this is a really important difference to get. The G4 track on the left is the living state of the particle. It's always changing. It basically answers the question, who am I, right this very second? But the G4 step on the right, that's a static record of the past. It answers the question, what did I just do? So the whole simulation is just this loop. Take a step, record what happened, and then update the track for whatever comes next.
So the big question is, how does the simulation decide what that next step should be? This is where the magic really happens. This is what we'll call the art of stepping. The brains of this operation is a component called the G4 Stepping Manager. You can think of it as the particle's own personal super advanced GPS navigator. Its one and only job is to look at the particle's current status, its passport, the G4 track, and make an intelligent decision about where it should go next.
But how does it know? I mean, this isn't just about getting from point A to point B. It's about a choice that's tangled up in all the complexities of physics. It can't just guess. It has to make the most accurate and, frankly, the safest decision possible every single time. So how does it do that?
Well, it does it by listening. At every single moment, it's listening to two key advisors. One advisor knows all the possible physics that could happen to our particle. The other one? It knows the map of the virtual world like the back of its hand. The final decision is always a negotiation between these two.
So on one side, you've got the physics processes. Picture them as a team of experts, and they're all shouting at the same time. One expert is for, say, Compton scattering, another for ionization. Each one yells out a distance saying, hey, based on my rules, an interaction might happen in this many millimeters. Then, on the other side, you have the calm, cool geometry navigator. It just looks at the map and says, well there, you're going to hit a wall in this many millimeters.
The stepping manager listens to all these proposals from all the physics experts and the geometry expert, and it follows one beautiful, simple rule. Step 1, physics proposes. Step 2, geometry proposes. Step 3, the shortest step wins. That's it. It's that simple. The simulation always chooses the absolute smallest distance that any of its advisors suggest.
And this is just so elegant. By always picking the shortest proposed step, the simulation guarantees it will never accidentally skip over an important event. It forces the particle to stop right at the point of the very next interaction or right on the border of a new material, whichever one is closer. It's a brilliant solution to an incredibly complicated problem.
Okay, so our particle has taken its step, it's arrived at its new location. Now what? Well, if the reason it stopped was because of a physics process, it's time for that interaction to actually take place. So a physics process is exactly what it sounds like. It's one of the rules from our virtual universe's rulebook.
It's the piece of code that says, okay, when a photon with this energy smacks into an electron, this is what's going to happen. This is the part of the simulation that can actually change things, the particle's energy, its direction, and it can even create totally new particles.
Now, you can imagine that if you had a bunch of different physics processes all trying to change the particle's passport at the same time, it would be total chaos. So, Geant4 has a very strict, very orderly system. A process isn't allowed to just go in and edit the G4 track. No way. Instead, it has to fill out a formal change request form.
And that formal request is an object called a particle change. The physics process that won the shortest step contest gets to fill out this form. It details exactly what should happen. What's the particle's new energy? What's its new direction? And, this is a big one, were any brand new particles, called secondaries, created in the event. The stepping manager then takes this neatly completed form and makes the official update to the particle's passport.
Let's make this super clear with an example. So here's our particle, just a moment before an interaction. It's cruising along with 10 MeV of energy, moving in a perfectly straight line, and right now, it's flying solo.
And bam, the interaction happens. The particle change gets processed, and the particle's G4 track, its passport, is updated. You can see its energy is lower now, its direction has been knocked off course, and critically, 2 new secondary particles have just been born. They've been added to the simulation, and each one now gets its own G4 track passport and will start its own journey.
So this whole dance, stepping, interacting, creating new particles, it can happen thousands, even millions of times just from that one initial particle. So how do we save this incredibly detailed story so we can actually study it later?
That's where the G4 trajectory comes in. See, the G4 track and G4 step are just temporary. They only exist while the simulation is actively running. The trajectory, on the other hand, is the permanent record. It's the complete life story of the particle, a list of all the key points on its path, from birth to death. This is the valuable data that scientists spend their careers analyzing.
But here's a little dose of reality, and this comes straight from the official Geant4 user guide. This quote points to a massive real-world problem. When one particle makes 2, and those 2 each make 2 more, you get this huge avalanche of particles called a shower. And if you try to save the full trajectory for every single one, well, you can run out of computer memory really, really fast. It's a constant balancing act between getting all the detail you want and what's actually possible to compute.
So after all this, why do we go through all this trouble? Because this incredibly precise step-by-step simulation changes the real world. In medicine, it's how we design radiation treatments that zap cancer cells while sparing healthy tissue. In space, it's how we figure out how to shield astronauts from dangerous radiation. And in fundamental physics, it lets us design massive experiments, like the ones at the Large Hadron Collider, to figure out what the universe is actually made of.
And that really brings us to the final thought here. We've just walked through the incredibly complex life of a single simulated particle. But today, scientists are simulating trillions upon trillions of them. So if we can understand our world with this much detail, one particle at a time, just imagine what new discoveries, what new technologies, and what new understanding is waiting for us just around the corner.